Welcome to the tutorial on Essentials to solve numerical of waveform synthesis using Laplace transform. In this tutorial, mainly we will see what do we need to know so that we can solve the numericals using the Laplace transform, wherein we have the representation of the signal in terms of a waveform. Firstly, we should know the three important singularity functions. That is, the first one is the unit step, second one is delta, and the third one is ramp function. Let us look into each of this individually. We have done a much detailed video earlier, but just for our understanding, let us see how we can represent the equations for the unit step function, delta function, and the ramp function. First one is the unit step function. The unit step function can be represented in this form. So if you look at the signal u of t is a signal which ranges from 0 and moves towards infinity. And this particular signal has an amplitude equal to 1. So mathematically, I can represent the signal u of t to be equal to 0 for t less than 0 and equal to 1 for t greater than 0. This particular signal u of t can be shifted in time. We can advance the signal or we can delay the signal. So if we want to advance this particular signal, say by a duration of a, that is t is equal to a, then I can draw this particular signal to be this way, having the same amplitude to be equal to 1 and advanced by a. If I consider the time units to be seconds, I can say that this particular signal u of t, it is advanced in time by a seconds. So this particular signal which is advanced in time is represented as u of t plus a. Mathematically, this can be given as u of t plus a to be equal to 0 for t plus a less than 0 and 1 for t plus a greater than 0. Similarly, I can represent this particular signal u of t to be delayed in time, and in this case let me consider again it to be delayed by a seconds. The signal is having the same amplitude 1, and this signal will be represented as u of t minus a. Mathematically, I can write this as u of t minus a to be equal to 0 for t minus a less than 0 and 1 for t minus a greater than 0. Now we have seen this particular signal being advanced in time and delayed in time. We have not seen anything with respect to the signal in terms of varying amplitude. So I can represent the signal u of t also in terms of varying amplitude. So say I have a signal with an amplitude equal to 2. So this particular signal can be represented as 2 times u of t, because you can see the unit step signal is having an amplitude equal to 1, but now we are having an amplitude equal to 2, so that is why we can represent this particular signal as 2 times u of t. So this particular amplitude can be in the negative side also. So when you have a negative amplitude, just put a negative sign. So this is regarding the unit step function. So let us look into the second one, that is the delta function. The delta function is also called as the Dirac delta function, or it is also called as the unit impulse function, and this is given as delta of t. Generally, this delta function is obtained by taking the derivative of the unit step function. So we can write mathematically delta of t to be equal to derivative of u of t. This is a very important essential thing that you need to remember, because it will be very much useful when we solve the numericals. So let us see how to represent this particular Dirac delta function. Dirac delta function is one which exists at time equal to 0. So if we are to draw this particular signal, we can draw this as a signal with an amplitude 1 which exists at the origin. So the area under this particular pulse, it's a pulse signal, is equal to 1. So we call it as a unit impulse function. And because this signal generally overlaps with that of our y-axis, that is why it is essential for us to represent this particular arrow mark and show the unit area. So we have written 1 adjacent to the arrow mark, because we need to show the weight of the signal and that the signal exists. So it's very essential that you mark the arrow mark and also represent what is the weight of this particular pulse. Now, as we have seen for the unit step, we can also have the Dirac delta function which is delayed in time or advanced in time, and we can also change the amplitude of this particular pulse. So let us see how we can do that. See, I have as an example, I have 3 times delta of t plus 2. So this is a signal that is being specified to us. Now if you compare the Dirac delta function that we have seen previously and the one which is given in this example, you can see that this is delta of t plus 2. T plus 2, whenever you have a plus sign, it means it is advanced in time, and you have 3 times delta of this particular function. So 3 times basically means you have to increase the amplitude by 3. So I can represent this as, if this is the origin, this is advanced in time, so it is here, and the amplitude is 3. Because this is advanced in time, so it comes towards the left side of the x-axis. This is minus 2. So I can write this signal as 3 times delta of t plus 2. We can also have in the negative direction, and we can also have the signal to be delayed in time. So let me consider an example. In this case, let me consider it as minus 5 times delta of t minus 2. So if you observe, the amplitude is negative and the signal is delayed in time, so it will come on the right side of the x-axis. So if I draw this to be the origin, this signal comes in the right side of the x-axis, but the amplitude is negative and it is being delayed by 2. So this will be minus 5 delta of t minus 2. So these are the ways in which you can represent a delta function: advanced in time, delayed in time, and variation in amplitude. Now moving on to the third singularity function, that is ramp function. So this ramp function basically is obtained by integrating the unit step. So I can write this function r of t to be equal to integration minus infinity to t u of tau d tau. This is equal to t times u of t. And this particular signal r of t is basically given in this form, r of t to be equal to a signal that passes through the origin having a slope equal to 1. Okay. So basically a ramp is a signal which changes at a constant rate. So like the way we had the unit step and the Dirac delta function, we can change this particular signal in time. That is, we can delay this particular signal in time, or we can advance this particular signal in time. So I can represent this particular signal r of t, one that passes through the origin, as r of t to be equal to 0 for t less than or equal to 0 and equal to t for t greater than or equal to 0. Now let us delay the signal in time and advance the signal in time and see what changes we can make. So first I will delay the signal. So let me consider this delay of about t naught in seconds. So I can represent this signal as r of t minus t naught. Okay, so in this case it will be 0 for t less than or equal to t naught, and it will be equal to t minus t naught for t greater than or equal to t naught. And similarly I can consider the signal to be advanced in time, and in this case it would be advanced by t naught seconds, and I can represent this as r of t plus t naught to be equal to 0 for t less than or equal to minus t naught, or t plus t naught for t greater than or equal to minus t naught. So you need to remember these three important singularity functions which will be useful in order to solve the waveform synthesis using Laplace transform. Mainly most of the waveforms that we will be studying will have the representation of the waveform, which would be a combination of unit step, a delta, or a ramp function. Other than that, we also need to remember the relationship between the singularity functions. The first one that we saw was delta function, which is the derivative of the unit step. So we can write delta of t to be equal to d of u of t divided by dt. And the second thing that we saw was u of t to be equal to d of r of t divided by dt. What we actually did was that we obtained the ramp signal by integrating the unit step, but what I have written here would be the reverse. So when we obtain the ramp signal by integrating the unit step, we can also write this as u of t to be equal to derivative of r of t. Let me form a table and tell you what would be some of the important Laplace transformations that you should remember while solving the numericals. The first one is that delta of t, we would be getting the signal in terms of delta of t, and this delta of t, when you take the Laplace transform of this will be equal to 1. U of t is represented as 1 by s. T is represented as 1 by s square, and we have seen r of t, right? R of t is nothing but equal to t times u of t, which is equal to 1 by s square. You should remember all these things because this would be very much useful, and why these properties or these functions particularly because we have a delta function which would be represented in terms of a waveform, u of t in terms of a waveform, t and r of t. Other than that, we also have some other properties in terms of sine and in terms of cos. So you can have e power minus at sine omega of t, which is obtained as omega divided by s plus a the whole square plus omega square. Then we have e power minus at cos omega t, which is equal to s plus a divided by s plus a the whole square plus omega square. So these are some other Laplace transformed pairs that would be useful if we are having waveforms which include the sine and the cos. Now, we have seen singularity functions and we have seen some of the important Laplace transform pairs. Now, other than this, what we should remember is that we should be knowing some of the properties. I will just tell you what you should remember. Mainly, the three important properties. The first one is the linearity property. So, as per this, what we have is that if you have two functions, say f1 of t and f2 of t, the Laplace transform of these individual functions, that is Laplace transform of f1 of t, can be represented as f1 of s, and Laplace transform of f2 of t can be represented as f2 of s. So as per this property, it is specified that when we take the Laplace transform of say a times f of t plus b times f2 of t, this particular thing can be split as a times f1 of s plus b times f2 of s. So this is the linearity property which will be very useful to us, especially when you have waveforms that have been combined together in amplitude. Second thing that we have is the time shifting property. So in the time shifting property, what we consider is that if we have the Laplace transform of x of t to be represented as x of s, okay, so if this particular signal x of t now is shifted in time and represented as say x of t minus t naught multiplied with the unit step function which is also shifted in time, then this will be equivalent to e power minus t naught s into x of s. This is one of the important properties and this will be very much repeatedly used in solving the waveform synthesis. Remember, here this t naught corresponds to the time shifted version of the signal, or it is delayed by what time. Okay. Moreover, whenever we are using this time shifting property, we will always be multiplying the signal with a unit step. So both the signal and the unit step function should both be delayed in time by the same unit. Okay. So if this is delayed in time by t naught, even this should be delayed in time by t naught itself. So only then this property can be used, otherwise it cannot be used. So you should remember this, both the signal and the unit step function has to be delayed in time by the same unit. The third property that will be very much useful would be the time periodicity property. So as per this time periodicity property, say let me explain it with a simple example. If you have a signal which is periodic in time, so let me consider this particular signal. Okay, so this signal is having amplitude A and it is repeating itself at t seconds. Okay, so this is a signal. let me represent this signal as x of t. So this signal x of t is actually having smaller versions of this particular amplitude, that is 0 to t, which is repeating itself after a duration of t seconds. So I can consider this particular signal or a part of this particular signal which is repeating itself as x1 of t. So you have the signal. The part which repeats itself is from duration 0 to t seconds having an amplitude a, and I am representing the part of that signal to be x1 of t. So as per this property, it says that when we want to compute the Laplace transform of this entire signal x of t, that can be computed as x of s to be equal to x1 of s, that is the Laplace transform of only this much part divided by 1 minus e power minus s into t. Basically this t corresponds to the duration of the part of the signal which was repeating itself. So I have represented in this case as t. But in general, if I have to consider the part of the signal which repeats itself, I can write that as t naught. Okay. So in this case, t naught is equal to t. So this is the generalized equation. You should remember, whenever you have been provided with a periodic signal, always consider the part of the signal which is repeating itself. First compute the Laplace transform of that and then use this equation wherein you have 1 minus e power minus s t naught, and in this case t naught is equal to t seconds if I consider the unit as seconds. So you should remember, for solving the problems with waveform synthesis using Laplace transform, you should know the singularity functions, that is the unit step, delta and ramp. Then you should be knowing the relationship between them, that is delta function is obtained as a derivative of unit step and unit step can be written as a derivative of the ramp. And you should be knowing the mainly the three important pairs, delta, unit and ramp. And this ramp can also be represented as t times u of t. These important Laplace transform pairs are very much essential. And finally, you should be knowing the three properties, mainly three properties: the linearity property, time shifting property and time periodicity property.